I generally record the classes and post them on YouTube. I don't always. Sometimes I just forget. But if you miss class and you just want to sort of catch up on what we did, then you can go to the screencast. Again, I don't guarantee that it'll be there. I'm usually pretty good about recording, but sometimes I have technical things or I just forget. Old quizzes and exams. Just every quiz and exam I've ever given in this class. You can find them there. These are just videos. This is the equation sheet. There's not a whole lot of math in this class. In fact, you probably look at this equation sheet, gosh, that looks like a lot of math. But there's really very little math in this class. There's a lot of mathematical relationships. Like we'll look at how variables respond to other variables, but not really calculations. In fact, you only need a calculator for any of the quizzes or exams. The calculations that you do will be so simple. It would be like 10 divided by 5 kind of things. All right, very little math in this class. But you do get the equation sheet on everything. For quizzes, exams, from henceforward, you get the equation sheet. So don't even bother memorizing the equations. You'll have them. You need to know they're there and that what's on there, but don't bother memorizing. And then this is just advice from past students who've made A's in the class. They read the book, they do well in the reading quizzes, and then when they do well in the reading quizzes, then, they do well in the exams too. And don't forget about the other things. Come into class with class participation. And then the project is there to help you. So if you're not doing well in those other things, then do the project. Everybody does the project, but it's generally meant to help your grade, not hurt you. Alrighty? That's exciting, right? Okay. Let's see. What I want you to do now is I'm going to have you guys come up. We're going to take photos of everybody. These are photos. In a minute, I'll put your names up on the screen, and then you'll come and you'll stand underneath your name like this, or however you want to stand. And I'll take a picture, and then the next folks will come up. It's in alphabetical order, except for one of you, which was at the beginning, and I added you late. I don't put these online. I print these out like on a sheet of paper. I put them in my notebook. I have an actual Facebook, not a Facebook account, but a book with faces in it and names. So it never leaves this building. It always stays on paper. Okay? I'm not going to post your pictures online. You trust me, right? If you don't trust me, or you just have some reason that you don't want me to take your picture, that's fine. Just don't come up. But it really helps me to know your names. All right? While I'm doing that, I want you to take a sheet of paper, and I want you to give me your name. So let me write it up here. Name. Your major. And listen, when I say major, don't say allied health, because allied health is usually a window into something else. Are you pre-OT, or SFA, are you PT, are you ultrasound tech? So tell me your major. I know practically all of you are allied health. Your name and your major, and then 3 things in your me bag. All right, those 3 things. Your name, your major, or your future career. Maybe is a better way to think about that. What is your future career? And then the 3 things that you would put in your me bag. All right, and then if Kenya, Deja, Adam, Kaylin, and Emily would come up. Adam, Kaylin, or Emily, and Kenya. No? Your Deja, is that, am I saying that right? Okay, awesome. All right, 1, 2, 3. All right, you're good. All right, Mallory, Madeline, right? Caitlin, and Bryce, and Cameron. All right. You're Bryce? All right. 1, 2, Awesome. Good job. Haley, Claire, Kaylee, Andrew, and Megan, do say? Claire? Andrew, Kaylee, Megan? Yeah. 1, 2, 3. Awesome. Christopher, Katie, Claire Graff, Morrison Hamilton, Skylar Hamilton. Here's Skylar. Here's Skylar. All right. All right. 1, 2, 3. Right, Chris? What do we call you? Okay. If you have a different name that you go by, if you could put that on your list, on your paper. Amanda, Christina, Bailey, Rusa? Oh, Ruth. You go by Ruth. Keelan? 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 Yeah. 1, 2. Bryant, Jillian, Taylor, Megan Lisco, Mallory Marino. Bryant? Sydney, Thurn, Julie, Samaya, Sarah, and Chriselle. Don't say anything. All right, 1, 2. Megan, Daranisha, right? Am I saying it right? Daranisha. Brianna and Madeline Arsenault. Anybody else that they call? This was the roll up for this morning. So if you're not on my list, then you're not. Okay. All right. So I also like to, on the first class, that we just get time for interview time. So like I'll learn more about you when I read your papers, but in this time you get to find out more about me. So you get to ask 3 to 5 questions, and not about the class, although I guess we can entertain things about the class, but really just sort of questions that you want to ask. You ever get to do this with your faculty? All right, let's try it out. And if you don't have any questions, we're just going to sit here for like 5 minutes and look at one another. Yeah. What's your favorite movie? My favorite movie? Let me watch that many movies. I mean, we've been watching Lord of the Rings with my son, and that's a good one. And my daughter, we just watched Little Women. The CBS Little Women. It's really good. Like, have y'all seen that? It's a 3-part episode. Yeah, but so I don't really have a favorite movie. Okay. Yeah. On our anniversary, we went to Baton Rouge. It was our 16th, and we just went to Baton Rouge and stayed the night. hung out downtown. We rode along the levee trail. We like to ride bikes. My whole family, we like to ride a lot. In fact, we have a tandem. Not just any tandem, but it's a recumbent tandem. It's definitely the only one in Thibodeau, but it's probably the only one in the southeast. You know what a recumbent tandem is? It's like you sit like this, and there are two seats on it. And then we went out, you know, nice dinners, and we sort of hung out with it. Yeah. I don't know. Think about bow ties. Like neckties are kind of expensive. But bow ties are really cheap. You can get like $3 or $4 on Amazon. And I think bow ties, they're easier to tie than a necktie. If I go without wearing a necktie for a couple of weeks, it's hard for me to remember how to tie it. But a bow tie, time to shoot. What else? Yeah. I'm from Mississippi, near Meridian, Quitman. My dad still lives there. My brother lives up there. I have two older brothers. One of them lives in Geismar. He's a welder. The other is, he does like AC work. He owns his own company now, but he started out as working on people's air conditioners. My dad's retired. My mom died about 5 years ago. I'm sorry, this is a lot more than you asked. But family history. My mom died about 6 years ago, 6 years in April. And my dad is now seeing a lady. She's super nice. I want them to get married. She's such a good husband. I hate for her to miss out on that. And he thinks he's going to die like in the next year. Let me roll my eyes. Listen, my great grandmother lived until she was like 95, and then his dad lived till he was into his late 80s, and he's only like 73, so he's got a good 10, 15 years left. Even though he smoked for most of his life and took really bad care of himself, he has no physical ailments. He's in pretty good health. You shouldn't smoke, it's really bad for you. Yeah.
How old are your kids?
Micah is 13. He's our oldest, our son, and then our daughter Ada, she's 10. Micah's 8th grade, going to 9th. Ada's 5th grade, going to 6th. Ada likes to sew. She's a really good seamstress. Like she makes her own clothes, she makes dolls. My wife started teaching her, and then Ada quickly got better than my wife, but now she just sort of, she has a lady that shows her things, but mostly she just sort of makes things. And my son really likes to collect things. It's not really us at all. Like my wife's not, we hate collecting things, but he has a really extensive coin collection. It's quite valuable, and if people give him coins, so if you have any cool coins. And he likes bottles, he likes Legos. Again, more than you're asking. Yeah, like
Your
you guys.
favorite genre of music?
Huh?
Your favorite type of music?
Oh, it sort of goes back and forth. Right now, I've been really listening to Hamilton. Did I listen to that musical? It's something. It's really good. And I'm not really that big into music. That's not my favorite part, but that's what I've been listening to the past couple of weeks. But I like it. What else? I guess I have more questions than most. Yeah. I don't know. I love teaching. I like the students. You know, I really do like teaching. I started in undergraduate. I see your hand. I started teaching it when I was an undergrad. We had like a teaching intern kind of thing. I don't think they have that in your department. But they do in chemistry. If you want to be a chemistry major, you can do that. You get to teach a college class. I found that I really enjoyed that. I don't think that I could teach kindergarten, for example. You would love to teach kindergarten?
My mom's a first grade teacher.
Really?
And my grandma was a first grade teacher. And mom was an 8th grade teacher.
Really? Yeah, I helped in my daughter and my son's class from 4th to 2nd grade. And I don't know, lots of kids vomiting and got their own hair. So you guys don't do that usually. Okay, yeah. Well, I started, if you really want to count when I was an undergrad, that was back in 98. But I've been here 13 years. 13? 14 years? And this is really my first real job after graduate school. I'm in the department I'm now, so I don't get to teach as much. You guys are like on my only classes. I have one other class. It's just sad, isn't it? Anything else?
Favorite color.
Favorite color. I may have a few. But my daughter is very trendy, and she tells me that mustard yellow and olive green are trendy colors now. Is that true?
Yeah.
And so like this bow tie, I'm not sure if you noticed that it has mustard yellow and olive green in it. I didn't buy it, my mother-in-law gave it to me because she's really trendy. Right? Trendy. Yeah. For a 70-year-old woman, she dresses like a 22-year-old, right? Rue knows her because she's from Finland. My mother-in-law is, and she just, they're the two, I'm sorry, is that okay to tell them?
Yeah.
They're the two twins in Finland. Alrighty? That's all? Physics 151? All right. So generally the way things work in class is let me see if my sound is working. Give me just a minute, okay? Okay, no, it's not working. I'll figure it out and get some sound in here. But generally the way things work in class is we will go through the workbook. Can I see your workbook? Yeah. And so in the workbook, it has sort of fill in the blank notes, and we'll go through that and we'll fill in the blanks. And then every so often you'll see a multiple choice question, and that'll be our clicker questions. So that'll be sort of the MO for every day. I don't let you out early, by the way. Like that's just, you guys pay good money to come in here, so expect to be here the whole time. If we get really far ahead, then I'll just cancel class for the day. In fact, we will have a day in February where we'll just have to miss because that's really good. But I don't let them out early because you're here and it's a baby, right? It's good. We'll be here. And then at the end of the semester, if we're ahead, then we're done. All right. So anyway, that's sort of how we'll work in class. These questions I pull directly from old tests and quizzes. So if you really want to get ahead, you can go and look up what the answers are, or just think of the answers beforehand and watch them, and you'll see them. Then I also will answer questions, or ask questions on the fly, too, as we move through. Alrighty? So we're going to sort of start with that. Let me get your papers, actually, before they get all shuffled away. All right. All right, so this first chapter is not in the book, but every other chapter that follows closely to the McCall book. But this first chapter is just sort of some introductory stuff about units and standards of measurement, how we measure certain things. So when one measures a physical quantity, anytime you measure something, all you're doing is you're comparing an unknown measurement to a known measurement. So for example, if I'm measuring my weight, I'm about 700 or so. 700 what? I'm about 700 newtons. Physics 151? Yeah. So if I measure my weight, what I'm doing is I'm comparing my weight, that is the force that's pulling down on me, to the force that's pushing back up on me. And I know that we'll see in chapter 1 that those two forces have to be equal, that the force pulling down, that's my weight, has to be equal to the force that the scale is pushing up. And so it's comparing an unknown measurement, my weight, to a known measurement, which is the reading on the scale. And inside the scale, there's a little spring that when you compress it, it knows the force that's required to compress it. We'll get into that later. But when you compress it, you know the force required to compress it. It measures how much you compress it, and then it translates it to a number that's on the scale. All right? All right. So all we're ever doing is we're measuring a known to an unknown to a known measurement. These known measurements are called standards. And 3 properties are required for a good standard. These things need to be true for a standard always. The first is it needs to be accurate. Now we'll look at some standards that have gone over time and look at are they accurate or not. We'll ask that question. The second is that it needs to be unchanging. And then the third, let's see, there's no 3 here, but list of 3, is that it needs to be accessible. It needs to be accessible to everyone. Now, we'll look at the measurements for length, mass, and time. Y'all see better that way? Yeah. We'll look at the measurements for length, mass, and time. In particular, we're going to be looking at the SI system of units. SI stands for, it's French, Système International. It's the international system. I don't know how to spell it in French. I guess that's right. Something like that. The SI system of units. And in that SI system, there are some base units that we use. I think there are 6 base units. But as far as we're concerned, we'll only look at 3 of the base units. That is the unit for length, the unit for mass, and the unit for time. In particular, we're going to look at the MKS. So this is a subset of the SI system, MKS. That's versus another system which is called CGS, and I'll come back and ask you what those mean. The current unit of measurement for length is what in the SI system? In the metric system, we also call it meters, right? It's the meter. So this current unit of measurement for length is the meter. And the standard has changed over time. In 1799, it was based on a fraction of the distance from the equator to the North Pole. It was about 1/10,000,000th. The distance from the equator to the North Pole. I'm going to abbreviate that, from the equator to the North Pole. So if you're looking at the Earth, you would measure the distance from the equator to the North Pole, and then to get a meter, you would take 1/10,000,000th of that. So let's think about these different properties. Is this an accurate standard for the meter? 1/10,000,000th the distance from the equator to the North Pole. Is that accurate? Is it a way to accurately measure the length of a meter? What do y'all think? No? It's not, right? Because it depends where you measure it. It's sort of hard to measure over mountains and measure across the sea. It's just a difficult thing to measure. So it's not accurate. It's also not unchanging because the Earth is not unchanging. The Earth is constantly shifting around. Sea levels change. It can change the distance from the equator to the North Pole. Is it accessible to everyone? You could argue that it is accessible, that everybody has access to the Earth. And so this first criteria, or this first standard back in 1799, misses out on the first 2. So if I were to think about these requirements, 1, 2, and 3, then it would miss out on number 1, number 2, and then you might be able to argue for 3 or not. But not a very good standard because it's not accurate and it's not unchanging. Until 1960, the standard was a bar in France. And not like a bar like the Red Goose Saloon or whatever, but a bar, an actual bar. A meter is about this long, it's about a yard. A metal bar that they kept in a lab in France, locked away that nobody could look at. All right, so that was our meter up until 1960. Let's think about this. Is it accurate? Is that if I have a bar and I say this is a meter, is that accurate? I see some no's and some yeses. Let me ask you a question. So what if you wanted to measure, I don't know, the width of your hair? Would a bar that's a meter long, would that be a good tool to measure that width? No. So it might be accurate if you just want to measure a meter in length, but if you want to measure either really small distances or really long distances, say like the distance from here to Pluto or wherever, then it's not very accurate. So not terribly accurate. Unchanging? Is that bar unchanging? You might be able to say that it is, but actually if I have a metal bar and I change the conditions in which it is, the temperature, the humidity, then that can change the shape of the bar. So not even really unchanging, because it's dependent upon the conditions that it's in. What about 3? Is it accessible to everyone? No, obviously not, because it's locked away in a vault in France. And that's sort of been the problem with our standards, is that they're just not accessible to everyone. So the bar in France is not accessible to everyone. All right, and now the current standard, and this is sort of the ideal standard that we have, is that it's the distance that light travels in a certain amount of time. I'm going to put the number, but you don't need to know the number. You just need to know that in this amount of time, which is 1 over 3 times 10 to the 8th seconds, that light will travel 1 meter. That 3 times 10 to the 8th, that's the speed of light. And if I divide that by 1, I get the distance. And it's 3 times 10 to the 8th meters per second. That means in 1 second, it travels 3 times 10 to the 8th meters. And so if I want to get the time for 1 meter, then I just take that value. Accurate? Yeah, because we know the speed of light really, really well. So it's a very, very accurate way to measure the distance of a meter. Is it unchanging? Yeah, as far as we know, that the speed of light doesn't change. And it hasn't changed for as long as we know. And we don't expect it to change. So it is unchanging. Is it accessible to everyone? You might disagree with this, but it is quite accessible to everyone, even people like you, just sort of normal people. It's not that hard to measure the speed of light. It's an undergraduate experiment for a physics major or a chemistry major to measure the speed of light. You might need some things like a little laser, you can pick that up somewhere, a little rotating mirror on a little motor, and then you can measure the speed of light. Very, very accurately. So it is accessible, it is unchanging, and it is very, very accurate. That's the epitome of standards, that you want something like that that's based on a physical constant. And the speed of light is a physical constant, something that's unchanging in nature. All right, now mass. Also, do y'all know what these stand for now? The MKS, CGS? What does the M stand for? What does the M stand for? Meter, yes. So M and then K and S, where we're doing length, mass, and time. So M is meter. What do you think K is? Kilogram, right? And S is going to be seconds. Right, so this is meters, kilograms, seconds. Kilograms and seconds. And then CGS is another subset of the SI system. Most scientists use the MKS system, but some scientists, like chemists and astronomers, I'm an astronomer, and health professionals will often use the CGS system. You didn't know this, but you use the CGS system. What does the C stand for? If M is meter, what is C? Centimeter, right. And then G, if K is kilogram, what's G? Grams, and then S is still the same. We have no other unit, or no other metric prefix really used for So health professionals, cc, right? Milliliter, that's a cc. It's a cubic centimeter. We use grams, so we use that usually in the health profession. So we'll see the CGS system again. Again, centimeter, grams, and seconds. Now, for mass, the current unit of measurement is the kilogram. In the MKS system, the standard is a cylinder in France. That's actually not true anymore. So I'm gonna write that, but I'm going to draw a line through it. This just changed a month or so ago. It's actually cylinder in France. That has a lot of the same problems as a bar in France, right? It's not accurate, it's not accessible, it's also not unchanging. That cylinder had a particular cylinder in France, said this is the kilogram. And anybody that wanted to measure a kilogram had to compare it to that kilogram. Because everybody decided that's what we're going to call our kilogram. Nothing else can be a kilogram. And so the cylinder in France has a lot of problems. It's fraught with problems. But last year, and this has been going on for about a decade, billions of dollars have been going into developing a new standard for the kilogram. One of the standards that they were thinking about was a sphere, a silicon sphere. And you might say, well, guys, if you just have a sphere that you define as your kilogram, well, isn't that a problem? Because then you sort of run into the same thing as the cylinder, right? You had this silicon sphere, they were developing it. Where do you think they were developing it? France, right? What's up with France? Anyway, they were developing a sphere, a silicon sphere, but the sphere wasn't the standard. What they were doing is then they were counting the number of atoms that made up that 1 kilogram sphere. And then the standard was going to become not the sphere. They were going to get rid of that. It was going to be the number of silicon atoms that make up a kilogram. And then all you need to know is the mass of a silicon atom. That one didn't make it. Instead, they used something called a watt balance. I have a video to show you, but unfortunately our sound's not working. But a watt balance, it compares a mass to a constant called Planck's constant. So the standard now is not a cylinder in France, but it is based on Planck's constant. Planck is a person's name. Using a watt balance. So the standard for mass, much like the standard for length, used to be an artifact. That is, it used to be some object that sat in France, but now it's based on a physical constant. Be careful on the old exams. If you look at the old exams and I ask questions about what is the standard for mass, it'll always be, this kilogram in France. But now the answer is different because it just changed a month or so ago. Now the standard is based on Planck's constant using something called a watt balance. It's just a normal balance, You know what a balance is to measure masses? Except when you put a mass on one side, it converts it to an electrical current, and then you measure that and relate it to the Planck's constant. That's good news. Billions of dollars have gone into developing this new standard. What's up with that? Why would we even care what a kilogram is? Or why would we even care to know a meter so accurately? Or why would we even care to know a second, which we'll look at a second, a second very, very accurately? You don't care? You don't really care, do you? Like if you're on your cell phone and you're talking to somebody around the world, you sure better have the timing set up correctly. Or if you use some of the modern equipment that you use as health professionals, you need to know those things very, very accurately because of the way the electrical systems work and the way the radiation or the detection systems or whatever. You have to know those things very accurately. And scientists around the world are working on these things. They all need to know what these measurements are that they're using over in France that we'll use here in the United States. So it is quite important. It's sort of foundational to our work as scientists, to your work as a scientist. And that's what you are. I know you don't feel like a scientist. That's really what you are. As you enter into a health field that is more and more and more based on technology. Okay? Billions of dollars, many billions of dollars over the years spent just on this. So you can get rid of this because this is no longer true. But the kilogram used to be losing mass. That artifact that they had in France was losing mass. All right, now for time, what's our standard for time, or what's our unit for time? Seconds is right. So the current unit of measurement is the second, MKS, CGS. The standard used to be based on the fraction of a solar day. That's accessible to everyone. It does change. Not terribly accurate. Not really a great standard. But now the standard is based on the frequency of a cesium atom. Or it's the period of an oscillating cesium atom. Or is all atoms vibrate back and forth, back and forth, back and forth. And some atoms vibrate at a very regular rate, like the cesium atom, a particular isotope of cesium. Very, very consistent in the frequency, the period that it takes to go back, forth, and then back again. That's what we call the period. And so the cesium atom has a very regular period, and we just say a billion of those vibrations will equal to a second. I don't know what the number is, but it's a lot of vibrations, and we say that's equal to a second. All right? You need to know those three standards. You need to know what the units are. You need to know what the current standard is. And then if I've given them to you, you also need to know what were the previous standards. Like, for example, with the meter, and then also with the kilogram, that you need to know that it used to be a cylinder in France, but now it's based on Planck's constant, using this watt balance. Okay? Again, this isn't in your textbook. Just here. You also need to know what makes a good standard. Let's try this question. So pull out your clicker. Which of these is a reason that a standard of measurement is not appropriate? So one of these reasons, one or more, would make a standard not appropriate. Which one is it? All right, let's do about 10 more seconds. Listen, if you don't know the answer, just guess. It's not really a big deal. Remember, if you get every answer wrong, that means you get the full 50 points for class participation. So if you're not sure, just guess. I'm going to take this away. 58. He is right. So remember, it needs to be accessible, unchanging. What was the third thing? Accurate, right. And so it needs to be unchanging. So if it changes, not appropriate. And then if it's not available to everyone, that means it's inaccessible, not appropriate. Does it matter if it's based on some obscure physical constant? Who here knew there was something called the Planck's constant before you walked in this room? A few of you. Yeah, okay. Well, it's not really an obscure constant, but it sort of is. The cesium atom, the frequency of the cesium atom, that's kind of obscure. Who knows that? The mass of a silicon atom, who knows that? Doesn't matter if it's obscure. In fact, it's better if it's a physical constant. And if it smells really bad, I don't think that any of our standards smell bad. Okay? But it wouldn't matter if they did. So E is the right answer. I'll also show you this question just to get used to these types of questions. You'll get used to my questions as you move through the different old quizzes and old exams as you prepare for the reading quizzes. But these types of questions where I have sort of a list of things and you have to pick out what's right or wrong, or sometimes I'll ask you to rank things. Those are common ways to ask multiple choice questions. And if you don't see them in this class, you'll certainly see them on various standardized tests that you take. Y'all take any standardized tests? You do for OT, right? Oh, y'all take the GRE? Oh, not the subject test, right? Just the general? Yeah. One day when I know you better, I'll tell you what I made on the subject GRE. Very interesting. It's bad. The physics GRE? Do not take the physics GRE. It's bad. But, all right. I want to look at dimensional analysis. Remember, we go until about 10. We get out here at 10:40. Is that right? 10:20. No, 10:40.
I got a class at 10:30.
All right. We don't get out early, so just sort of be prepared for that, and not any day. So if you don't want to stay the whole time, just don't come. All right. So dimensional analysis. We're going to do this because this semester we'll work a lot with mathematical relationships. So there's not a lot of math where you're calculating things, but there is a lot of, if I change this variable, what happens to this variable? And so it's useful for you to be able to manipulate equations a little bit. You all had algebra, I know, or you had something like that in high school, or maybe even here at Nichols. But there's not a lot of complex algebra in this class. I don't want to scare you off. Don't go drop the class right now. There's not a lot of math in this class, but you do need to be sort of familiar with how we move variables around in an equation. And this will help you do that. And dimensional analysis is also a great way to check or solve a problem, because what we do is we look at the dimensions of the variables and compare that to other variables that are in the same equation. And then if they compare and they match up, then we know that that equation, at least the variable, the units match up. And so it's a pretty good indicator that it's a correct equation. So let me first just give you some common dimensions and their units. So area, you probably know all these, but area is in square meters, right? Meters times meters. Volume is cubic meters. Meters times meters times meters. Velocity is meters per second. And then acceleration, that's how our velocity changes. It's going to be meters per second. And so we express that as meters per second squared. And then, I'll give you a few here. I'm going to do let's just try this one. So x equals vt. X is a distance, that's in meters. V is a velocity, that's meters per second. And then t is a time, that's second. And so what you want to ask is, are the units of this equation dimensionally correct? That is, are the units on this side equivalent to the units on this side? Y'all click in and tell me, is it A, yes, or B, no? This equation is dimensionally correct, A, or it is not dimensionally correct. That is, the dimensions on both sides are the same. Is it correct or not correct? Feel free to ask your neighbor what they put. In fact, I encourage you to do so. About half of you have it correct, and half of you have the incorrect answer. So ask your neighbor what they put, and if you want to change your answer, you can. Take just a few seconds. No, y'all dug in? Or you don't want to ask? It's all right. But you can ask. Feel free to talk to one another. I'm going to stop here at 49. Okay, this is a dimensionally correct. And the way that I know is I look at this side, and it's meters. And then I look at this side, it's meters per second, and then it's multiplied times seconds. And notice I can cancel out those seconds. You got that? Yeah. Let's try this other one. I just want to point out a couple of things, though. I know x is meters. But what is this? X with a little 0 subscript. Have you ever seen something like that? We call that, what is that? You're right, it's initial. It's shorthand for X at t equals 0 seconds. And so we just, in physics, we use that subscript 0 as the initial condition. What was the initial position for this object? X is the position at a time t. X sub 0, or X naught, we call it, naught. Not British, but it's naught, like N-A-U-G-H-T, meaning nothing or 0. X naught is the initial position. So while this has meters, what are the units of X naught? No, it has a unit. Everything has a unit, or most do. What are the units of X naught? If X is meters, what is X naught? It's also meters, right? Not a trick question. So here I have X naught is also meters. And then sometimes we have constants in our equations, like I have that 1/2. Usually, when I have values like that, they have no units at all. So when I'm thinking about, is this equation dimensionally correct or not, then I would just say, I'm not even going to worry about that 1/2, because I'm not worried about the values here. I'm just worried about what are the overall dimensions. And what you need to determine is, are the units here the same as the units here, here, and here? And if any one of those is not correct, or is different, then it's not dimensionally correct, because it's like adding apples, 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 oranges, if the dimensions are different. All right, let's try it. A, yes, B, no. Now, really, I've already told you that these two units are the same, and you also know that these two units are what? The same or different? Same, because it's just this one, right? So really, it's this term that you're worried about. That A times t squared, where A is acceleration and t is time, does that have units of meters? That's really the question we're asking. If it does, the answer is A. If it doesn't, the answer is B. All right, let's do about 10 more seconds. Y'all doing a little better on this one? Wait. Sorry, no you're not. You're doing about the same. But feel free to ask your neighbor. They might just have the right answer. All right, we'll stop at 105. 105? Yeah, boy, we are riding the fence on this. The answer is A. It is yes. We already know that X is meters. X naught, which is just the initial position, is also meters. VT, that's meters per second times seconds, plus AT squared, that's meters per second squared. T is seconds, and then it's squared. So look, I can cancel some units out, like that. And I'm left with meters, 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 all the way throughout. And so yes, that equation is dimensionally correct. All right? Again, what I'm doing is when I sort of jog your algebra skills a little bit, because I know they might be a little rusty, you will see some questions that are similar to these on the first exam, but we're not going to have a whole lot of math throughout the semester, so don't freak out. All right, I think I have another question over here. A little more complicated. Let's try this one. Is this one dimensionally correct or not? A, yes, B, no. I'm going to help you with this A over T. I would write this, when you write A over T, write it as A times 1 over T. And then that's going to be meters per second squared, 1 over seconds. Because A is meters per second squared, T is seconds, but it's 1 over T, so it's 1 over seconds. Oh, I'm sorry, I didn't start it. I'll start the clicker base. So if you didn't get your answer in, go ahead and put it in. A yes, B no. Feel free to ask your neighbor. You know, about half and half right now. All right, let's stop at 25. 25. All right, let's see how we did. All right, so B is the right answer here. And the way I would know that is I start out, well, this is meters per second. And you know, I'm going to skip over the A over T because I look at that last term and I know that this is meters and that's seconds. So I already know right now I can just say not correct, right? Because the units here are not the same as the units here. But then let's look at this one as well. What are the units of that A over T? Meters over what? Seconds. Not squared. Cubed. Right, because I'm multiplying meters per second squared times 1 over seconds. All right? Good job. So these have different units all the way throughout. This is different from that, different from that. Not a correct equation. If you encounter something like this when you're looking in the course of equations and you say, no, that can't be right. Again, you'll have 1 or 2 questions on the exam that will be just dimensional analysis. But just being able to do that sort of work will help you on other things. If you're not very good at this, and like half of you aren't, that's okay. Don't worry, we'll develop those skills as we go along. And then by the end of the semester, man, you have some mad skills, like mad algebra skills. Right? Are you excited about that? You should be. All right, let's try these questions. The one on the left is a little bit different. I want to know what are the units of P. I give you the units for G and F. What are the units of P? All right, let's stop at about 50. 5 more seconds, just guess if you're not sure. I'll move on to the next one if you. All right. Okay, good. D is right. Meters per second. P is, I want to know what P is. It's equal to F over G. F is units of meters. G is units of seconds. And so my units for P are meters per second. Alrighty? Listen, I read in the paper today about this guy that was in an accident, and it was really bad. His left arm was basically detached from his body, and then his left leg, basically, he lost his entire left side of his body. Did y'all read that? He's all right now. It's a joke. It's a joke. He's all right now. When y'all do well on clicker questions, I'll give you a joke. And you did well on that clicker question. Okay. All right. Let's try this one. Many of your questions will just sort of be like this recall. What is the standard for the second? What is it based on? You can look back in your notes or ask your neighbor. All right, let's stop at 30. Stopping at 30. 5 more seconds. Okay, let's see. Yeah, D. You'll need to know these, okay, because the standards will be on the exam. I'll ask you what are the standard for the length, mass, or time. And the standard for the second used to be a certain fraction of the solar day, but now it's the frequency of the cesium atom. And I understand why some of you put B. That's why I put B there, because this is not the standard for the second. It's actually sort of like the standard for the meter, right? The meter is the time, or is the distance that light travels in a certain amount of time. Make sure you know those standards. You'll see a couple questions on the exam related to the standards. Both what are the standards, or the units, and then also what makes a good standard. Okay? I'm not sure how you guys study. I like to make note cards. So buy you some little note cards. They're cheap note cards. Those 3x5 note cards, and then you can even cut them in half. And when you find sort of main ideas like that, just write them on your note card, and then you can just flash through them. All right? Working through the old tests will also help you a lot in this class. Work through those old tests. They are good practice. I usually write completely new tests, though, so don't throw reliance on those tests, because you'll see different but similar questions on your exams. Okie dokie? All right. Let's look at these unit conversions. So we'll use dimensional analysis to convert units. So let's say, for example, I want to convert 24 meters per second to miles per hour. And the way that I'm going to approach this is I'll look at the units of my different values, and I'll create some conversion factors. And my conversion factors will convert meters to miles and then seconds to hours. So I need to know how many meters are in a mile, and I need to know how many seconds are in an hour. How many meters are in a mile? Anybody know? Roughly how many meters? Anybody run track? Nobody runs track in this room? You're right, 1600, or 1609 to be exact. So there are 1609 meters in 1 mile. And then for seconds, by the way, I'll provide you with conversion factors. So you don't need to know this number. I'll give this to you. I won't give you the seconds in an hour. We should be able to figure out that. See, how many seconds are in an hour? Well, I know in 1 hour there are 60 minutes, and then there are 60 seconds per minute. So that means there are 3,600 seconds in an hour, right? Because I got 60 minutes in an hour. Each minute is 60 seconds. So there are 3,600 seconds in 1 hour. So 3,600 seconds is equal to 1 hour. So now those are my conversion factors. I'll use those to convert this unit. So I have 24 meters per second. What do you want to do first? Distance or time? Distance. Let's do distance. So I'm going to put my conversion factor here. On the bottom, I'll put something that cancels out with meters. So I'm going to put meters in the bottom. What number is going to go on the bottom? It's the 1609 number. Right, so 1609 meters, and then in the top I have 1 mile. And then later I'll come back and cancel out these units. And notice now, if I just do this, I'll be left with miles per second. But I don't want miles per second. I want miles per hour. And so I do, what goes in the numerator? That's the top. Hours or seconds? Seconds, right. So 3,600 seconds over 1 hour. That gets rid of the seconds here and here. And then I'm left with miles per hour. And then I do that calculation. It works out to be 54 miles per hour. Or 54 mph. Okay? Not Morris P. Hebert, but miles per hour. Anybody know Morris Hebert? No. All right, let's try this one. Irene is 2 meters tall. She's pretty tall. Building is 10 meters tall. How tall is the building in Irene's? That is, if you were to stack Irene, one on top of another, how many would it take to measure the full length of the building? Now doing awesome. I think just one person, a couple people have the wrong answer. So ask around, ask your neighbor. You'll probably get the right answer. All right, I'm going to stop at 43. Look at y'all. E is right. That's 5 Irenes. And the way that we would do this is we would say 10 meters. Now, y'all probably just thought about it, right? It's 10 meters. She's 2 meters. Takes 5 of her. But really the consistent way to do this is I would do my conversion factor. 1 Irene is equal to 2 meters. And so I say 2 meters, 1 Irene. And so this is going to be 5 Irenes. You want to get in that method, that consistent method. That way, when it's not so obvious, you still follow the same procedure. And there are other problems in the old test. All right, let's try this last one, then we'll wrap it up. What is the unit for mass in the Système International Convention? We're assuming an MKS. Whenever I say SI, I'll assume MKS system. What's the unit for mass? All right, I'm going to stop at 38. You are awesome. What did the fish say when it ran into a concrete wall? Damn. Sorry, that's a vulgar joke. I'll try to keep those to a minimum. We will have a reading quiz on Tuesday on the very first section of Chapter 1. That's just the physics section of Chapter 1. We're going to get into that a little bit on Thursday, but we certainly won't cover the whole thing. If you want to go start reading Chapter 1, the first section is the physics section. We'll do a reading quiz on Tuesday, a week from today. Have an awesome day. Yeah.
So I had surgery.